Lecture 6.1, Day 2, Euler's Method. This is the First Peoples Buffalo Jump State Park near Great Falls, Montana. This is where for hundreds of years before the horse came to North America, Native Americans used to hunt buffalo by luring them and driving them over this cliff. Leonhard Euler was a Swiss mathematician who made a huge number of contributions to mathematics, almost half after he was totally blind. When this portrait was made, he had already lost most of the sight of his right eye. It was Euler who originated or popularized the following notations: f of x, or function notation, e as the base of natural log, I as a square root of -1, the summation symbol, delta y for finite change, and, believe it or not, the pi symbol for pi. The pi symbol was first used in 1706 by Welsh mathematician William Jones, who lived from 1675 to 1749. However, the symbol was not in common use until 1748, when Euler used it in Introductio in Analysam Infinitorum. There are many differential equations that cannot be solved. We can still find an approximate solution. We will practice with an easy one that can be solved. dy dx equals 2x, with an initial value of y sub 0 equals 1. We make a table with n, x sub n, and y sub n. So after 0 iterations, we start at a point where x equals 0 and y equals 1. So we put that dot on our graph. Now, dy dx is 2 times 0, or 0. But remember, dy dx times dx would be dy. So we'll let dx be 0.5, a small change in x. So then dy is 0. That is dy dx times dx. So we have y sub n plus dy equals y sub n plus 1. That is, we add the change in y to the previous y to get the new y value. So y sub n plus 1 is still 1. So after one iteration, x is moved over a distance of dx, or 0.5, and our new y value is 1. So we plot that point. We find dy dx again by putting 0.5 in for x. So dy is 0.5, and y sub n plus 1 is 1.5. So after 2 iterations, we are at 1.5. And we repeat the process, finding a new value for dy dx, multiplying by dx to get dy, and adding that number to the previous y to get the next value of y. So after 3 iterations, we're at 1.5, 2.5. We'll do this one more time. So after 4 iterations, we're at 2, 4. Notice that the x value just increases by the value of dx each time, which in this case is 0.5. The exact solution to this problem can be found this way. We start with dy equals 2x dx. Take the antiderivative and get y equals x squared plus c. Putting in our initial values, we find that c equals 1, so y equals x squared plus 1, which gives us a parabola. This is called Euler's method. It is more accurate if a smaller value is used for dx. It gets less accurate as you move away from the initial value. So if we look at these two graphs, if you measure the error vertically, you see at first the error is not very great, but when we get to x equals 2, the error in y measured vertically is quite a bit larger. The TI-nspire has Euler's method built in. For example, dy dx equals 0.001y times 100 minus y, where y0 equals 10. We press Menu, 3, Graph, Entry, Edit, 7, Differential Equations. We enter the differential equation as 0.001 times y1 times 100 minus y1, with an initial value of 0, 10, and then press Enter. We need to adjust the viewing window. Press Menu, 4, Window Zoom, 1, Window Settings. Make appropriate changes to the viewing window, and then press Enter. And we see our graph drawn with Euler's method. Warning: the TI-nspire has an upper limit to the number of iterations it can plot for Euler's method. If you make the window too wide, the calculator will not graph the curve. If this happens, you can either choose a narrower window or change the plot step to a larger value than the default value of 0.1. Press the Tab key and scroll up to get your differential equation. Then click here. we get a screen where we can adjust our settings for differential equations. Scroll down and change the plot step to something larger. You can try other initial conditions by using the Tab key to get back to the equation entry page. This time we'll click here. Use the Tab key and input new initial values, then press Enter. And we see a second curve with different initial values. You can also use the trace function to investigate the curve, or you can grab the initial point and drag it to a new position. The book refers to an improved Euler's method. We will not be using it, and you do not need to know it. The calculator also contains a similar but more complicated and more accurate formula called the Runge-Kutta method. You don't need to know anything about it other than the fact that it is used more often in real life. This is the RK solution method on your calculator.